Okay, so I guess we can start the class. Oh, probably before, like, remember we have one more class before the break. So we only meet on Monday of next week. Um, so I hope that, I mean, definitely I'll give you your exam grades before Wednesday, which is when the break starts. And probably the information for the next midterm will be posted sometime like on Monday. Oh, they were well. They went well, I think. You are the ones who can tell me. So, uh, but no, yeah. It doesn't look like the grades will be lower than the previous exam, which is good because this tends to be like the, worst exam in terms of grades, just because triple integrals kind of kills a lot of people. So it looks like you survived. The final will be cumulative, correct? I mean, it's more, I guess it's more biased towards the end of the course. Like there will probably be more integrals that like integral problems like than other types of problems. But yeah, the idea, there's like a midterm on December 6th and then the final. The final is December 16, if I have it correct. No, I don't think I ever said 20th. It should be the 16th, but I can double check that. Pretty sure it's on the 16th. We do have class next Monday. Well, depends on what you mean by next Monday. Not on the Monday of next week, but not the Monday after the Thanksgiving break, right? So it is the 29th that we don't believe, because there's like this swap with the schedule. So there is a Monday that we don't have class, but we are meeting the upcoming Monday. So yeah. Basically, we'll have covered most of the material for the midterm by Monday of next week. There will be like a section left that we won't discuss, but what I will do is post like a video from the last semester, of the Zoom video from last semester, in case someone wants to watch it before the break. But obviously we will cover it after the break. But I mean, if someone wants to like look at all the material before during Thanksgiving break, I'll post like that Zoom video. Yeah, it's one midterm and one final. Well, the Thanksgiving break starts on Wednesday, I thought. Right. No, I thought that it was the other way that we can check like on the Rutgers calendar. Just give me a second. Yeah, I think next week should be normal. Oops, not this Safari, this other. Yeah, if you see here, the change in designation is on the 29, and the Thanksgiving break starts on the 24. So last time, just to recap what I told you, the idea is that if you like, you can think that you have like a box, and you are like moving the box from some initial position to some final position, right? So the final position is like the dotted box. And so in order to move a box, obviously, like you have to choose like a path that you want to carry this box through. So you could choose this path, but someone else could choose something more complicated. And another person could like go more like something like a straight line, right? So there are many possible paths that take you from one place to the other. If you think that you were like applying like a force along this path, right? So you have like this force vector. I don't know the particulars of how it would look. So I'm just drawing some random arrows, but just think that that's like represents at every point of the path, the force that you applied to the box, okay? There could be additional forces, but we don't care. And so the work done by this force, remember the work done by F is just, well, if you call any of these paths C for curve, the way in which it is denoted is just as an integral over C of the dot product of F with the R. But again, like in practically speaking, like the way in which we can compute it is by taking the dot product of F with the velocity vector and integrating this over time, right? So that's like last time how we were computing work. The last example that we did was just to show you that the work not only depends on the endpoints, but in general, it depends on the path, on the particular path that you chose, right? So there's no a priori reason for why the work along the red curve has to equal the work along the green curve or the work along the brown curve, despite the fact that they'll both the three curves share the same initial point and the same final point, right? And so there's actually a very special case called the case where the force is conservative, where actually this does occur. And so a force will be conservative if the work only depends on the endpoints and not on the particular trajectory that you chose to go from one point to the other. Okay, so this is what we're going to spend all of today, basically. So F is conservative. If the work done by F depends only on the endpoints and not the trajectory chosen connecting these 2 points. Is that making sense? Okay, so again, like you should think of being conservative here as a very special property. It's not something that like a random force would satisfy. So it's like a very like unique feature, and you'll see that it's very useful. So like the first, and again, like we're kind of close to the end of the course, there are a couple of things that I'll just like give you like what you need to know. Like if you want more details, like you can look at the YouTube videos, but we are kind of like, you know, have to wrap up a couple of things left. So like some of the things I'll tell you right now are like a bunch of black boxes. Then you just have to take my word that this is how it works. I mean, maybe towards the end, I'll say a little bit more of why it works this way. But for now, I'm just giving you like the hammer to like to solve this the problems that we need to solve. So like the first thing that you have to like you may be interested in is like how can you check in practice if a force is conservative? So that's what the first thing that we're going to talk about. So how can you check? So So here's question 1. How can you verify whether f is conservative or not? Okay, and the first thing that we have to do for doing that is compute something that's known as the curl of f. Okay, so the idea is that f will be conservative if the curl of f vanishes. And so like the first thing that I'll tell you is right now is what this curl business is. So what is this curl stuff? And this is something that you'll see if you ever take like a course like in like one of these physics courses like in electricity and magnetism, because it's like sort of like the curl of like things like the electric field are like the stuff that appears like in Maxwell's equations for electromagnetism. So what is the curl? And again, this will be a black box. So let me draw it here. Well, the curl of f this is a new vector. Like, so we're going to produce a new vector. Okay, this is a new vector. How do you compute it? Well, think of f. F itself was a vector, right? Because it's like a force. So it has like components. So if you think of f as having like components, let me call them f1, f2, and f3. So again, like as a vector, these are like the entries of the force. Then the curl is like, what does like this notation reminds you of? Ignore this cute delta triangle or bit set slice. Like it, well, like the triangle reminds you of gradient. This is good. And what does like the thing in the middle reminds you of? The cross product, right? So in fact, we will compute it as some sort of cross product. Okay. So the curl of f will be the following. I don't know if you remember, we did this trick for computing cross product where we would like do like a 3x3 array, like a matrix. Okay. So if you remember the cross product in the cross product formula, you know, the last row would have like the entries of the second vector. So here we would put like f1, f2, and f3, and then in the second row we would put the entries of the first vector. So the trick is that strictly speaking, this is not a vector, but I don't know if you remember how the gradient was computed. The gradient of a function was computed by like taking partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. So somehow we're going to take the partial derivatives as quantities that we enter into the matrix. So what I'm trying to say is that what we're going to put here is the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. And I'll tell you in a second how this is supposed to work.
Is that of the function f?
No, right. Like that's the thing. Like they're like ghost quantities. So just the partial derivative itself, just like it's floating like naked. It's not like next to anything else. It's just partial derivative. Like for example, yeah, there is not like partial derivative with respect to x of something. No, it's just like the partial derivative with respect to x. It's one of these
So
things.
is what we're doing essentially taking a partial derivative with respect to x, but with the z function?
Well, so
Like
what
we're
like
changing.
yes, the mystery. Let me do it with an example because I think this would just like break all the mystery. So it looks kind of like weird at this moment, but it's just like the best way to remember how to compute the curl. So that's why I'm writing it this way. So just give me let me write you an example and like you'll see how this is supposed to work. In practice, like once you know how to find it, like there's no source of confusion. But I do agree that this looks kind of odd. So let's just do like let me explain like how to do it with an example. So let's say that f, right? Let's say that f is a vector x y squared z, x squared y z, and then c squared. Okay, so again, like f is like a force, and like I don't know if you remember like the animation I showed you last time, like the force can be changing from point to point. So in general, you should think of f like as something that could depend on x, y, and z. So it's meaning that it's not like a constant force. So let me put it this way. So what I'm trying to explain now is what's the curl of f, right? So if you just follow the thing that I just wrote, right? It would be I, J, K. You just do this weird thing where you copy these partial derivatives and then you put the entries of the force. So you put x, y squared, c, x squared, y, z, and then z squared. Is this so far so good? Like how at least how to write it? I still have to explain how to compute it, right? But is it making sense? Like at least how to write this down? So now, what we're going to do is like try to see what you should get if you apply like the rule that I thought taught you for like computing the cross product. So like if you remember the cross product rule, like the idea was to remove like a row and column, right? And so let's see, this should bring you back to the beginning of the course. So here you remove the row and column, the first row, first column. And so you get I, right? And then you would have to put like the determinant of this 2x2 matrix, right? But the determinant of this 2x2 matrix, what would it be? It would be the partial with respect to y times c squared, right? So you sort of write it as if you were just going to do a multiplication. So just just write it as like as a product minus the partial with respect to z times x squared yz. Okay, and so that's like sort of what you would get if you were doing like the determinants formula. Like the only thing that you have to take care of is that you always put the partial derivative first, you know, when you write it, because like what this is going to mean is that we're going to take the partial derivative of z squared with respect to y, and then we're going to I mean, what I'm saying is that it's if you just wrote c squared partial with respect to y, then that's not really good, because you have to put like the partial derivative like as the first factor of the product. But besides that, there's not anything different from what we were doing. Is that making sense? So let's see. Remember, it was plus minus. So the next entry would be minus j. So for minus j, you deleted this row and this column, right? So
Professor,
yes.
sorry for disturbing. Well, one question. So when you say d over dy z2, do you mean like what exactly does that mean?
I mean that you're going to find the partial derivative with respect to y of c squared, which one is going to be 0, right? Because c does not depend. If in fact, if you want, like before finishing writing everything up, let me just say what this should be, right? This should be 0, right? Because this is like the ordinary partial derivatives that we saw a couple of weeks ago, right? And what should be the partial derivative with respect to z of this quantity? It should be x squared y, right?
Yeah.
So that's basically what you have to do. So I just mean, like, think of this as functions. And so you take the partial derivatives of these functions, right? This is like the function c squared, and then you get 0. And this is like the function x squared yz, whose partial derivative with respect to z is x squared y. Is that making sense? So
yeah, got it.
Yeah, it's kind of, I mean, again, like it takes some time to get used to it, but at the end, it's not that bad. So like, again, for like the entry with respect on j, remember you have to delete this row and this column. So you get what? Partial derivative with respect to x of c squared minus partial derivative with respect to z of x y squared z, right? So again, before keep going, we can already compute these quantities, right? Like, so what should be the first term here? Compared, just following what I said before. 0, good. And what's the term here? XY squared, right? And finally, there's plus k. And so for the plus k term, like again, you deleted this row and this column, right? And so you have to do the determinant. So you do the determinant with respect to x of what? Of x squared, sorry, the partial derivative with respect to x of x squared yz minus the partial derivative with respect to y of x y squared z. Is that making sense? Good. Yes, this is what, excellent. So this is 2xyz, and this is 2xyz. Is that okay? Is this calculation of the curl making sense? So again, think of it as some form of witchcraft. I mean, I'm not going to, like, at least not today, I'm not going to tell you why we're doing this, right? We're just doing it. But it ends up being like the right thing to look at. Ironically, the way to understand why this is like the right thing to look at is that we need like the theorems at the end of the semester, which are called Stokes theorem and Green's theorem. But for now, it's just like the, you know, like learning how to do things, and then you think about what it all means. So what do you end up getting in the end? Well, this 0 no longer, yeah, you don't have, well, let me write like the answer. So you would put minus x squared y times I, right? So minus becomes plus here. So you would put xy squared times j. And here for now, you can put 0k if you want, right? But so this is the same as the vector x minus x squared y, xy squared comma 0. Is that making sense? No, they don't necessarily, like the term with k, like sometimes will be not 0. It's like a particular like example. So sometimes like this could be 0 and the other two are not 0. and things like that. So there's no rule on which one should become 0. Okay. Is that making sense? So you see, like you did get like a new vector. So this is what is called the curl of F. So you got a new vector. And the point is, like what I told you, is that the condition for F to be conservative is for the curl to vanish, right? So what does it mean for a vector to vanish? It requires all the entries to be 0, right? So, like the idea is that since not every entry of the curl is 0, right? F is not conservative. Okay. Is that making sense? So like, again, like, and this is like always a criteria that you have to do. If someone hands you like a vector and they ask you, is it conservative or not? You find its curl, and only when all the entries of the curl become 0, 0, 0, you can say that the vector F is conservative. So you see, like it requires a lot of partial derivatives to vanish. So that's why it is not that easy to achieve, like as a condition. Is that okay? Yeah. It can be described graphically. Let's see if there's one that like, I mean, so let me like well it has to be, well, you wouldn't so like just to first answer like the representation of the curl, like essentially what the curl will tell you later on, I'll show you some animations maybe later, is that the curl, when the curl like the curl sort of measures whether or not the vector is sort of like spinning around. So things with 0 curl are things that are not spinning, and things with non-zero curl are things that are spinning. So so like, I don't know if you remember, like if you think of the, let me do an example, maybe another example where like the curl will not be 0. So, and maybe this will, and then I'll show you the GeoGebra animation.
One question.
Yes.
Where do we use this in like a daily basis kind of thing? Like, where would we be able to use these? Sorry,
Well,
but like remembering those like somehow helps me understand a lot more of the stuff.
well, the thing is like, well, it depends on whether you actually will end up using it, but like there's like this, what I was saying, if you ever take electricity, like, you know, like an electrical engineering class or whatever, you know, there's like a thing called like the electric field, and there's also a thing called the magnetic field, right? And so like, you know, there are like 4 equations describing, you know, there are like versions of Newton's laws. You know, Newton's laws are like for how force acts on an object, right? But there are like equations like analogous to Newton's laws saying like how the electric field and magnetic field behave, and those are called Maxwell's equations of electromagnetism. So there are 4 of those, and like the equations of Maxwell actually involve like the curl, like our friend the curl, for example, of the electric field. So there's like, they sort of like are operations that sort of appear like when you have to write the equations of electromagnetism. And so, in fact, let's see. Here you go. If you go to Wikipedia, then, oh, here it is. There's like one of these equations, right? So this is one of the 4 equations. And so this is an equation for the curl of the electric field. And this is, there's one of the other equations is an equation for the curl of the magnetic field. And then there will be two other equations, and these involve another thing called divergence, which we will also study. And this is like, eventually, this is how Maxwell figured out that light is an electromagnetic field, like a similar from, I mean, it's like a long story, but this is like the beginning of like modern telecommunications, like, you know, cell phones and other things cannot really work without understanding electromagnetism. So also, current civilization depends on Maxwell's equations, basically. They're like the four most important equations of the discovery in like the 19th century, basically. So. Whether or not you end up using the curl in your life, well, it is in your cell phone secretly. So let's do an easy one, but this will be in like just to compare like representations of the vectors. So what's the, and so here's another example. What's this vector? The curl of this vector again is I, j, and k, partial x, partial y, partial z, and then minus y, x0. So this gives you, again, if you do all the stuff, it gives you I partial with respect to y of 0 minus partial with respect to z of x minus j partial with respect to x of 0, minus minus becomes plus, plus partial with respect to z of y. Sorry. Yeah. And then plus k partial with respect to, oh good, partial with respect to x of x plus partial with respect to y of y. Is that making sense? Are there any questions about how I found the curl? Does the calculation look fine? So you get like, what are we getting? What do we get in the component for I? Oh, there's yeah, it's just that, like, remember, like for the determinant formula, in the determinant formula, there's a minus of the formula. And since this one already had a minus, the minus minus becomes a plus. And remember that it's plus I minus j plus k. So that's why the signs alternated for I, j, and k. But yeah, the reason, like, it's similar. There's also like, that's the same explanation for why there's a plus here. Because when you look at the determinant formula, right? When you do this term, there's a minus of the formula, with the minus becomes a plus. Is that better? So in this case, the curl for this vector is 0, 0, 2, right? So maybe this will help you answer like this visualization question that someone had asked before. Let me show you how this is supposed to look like. So just give me a second. Can everyone see the GeoGebra?
Yep.
So good. So the components for this vector were negative y and then x, right? So this is what I'm entering here. Do you see it? So if you think of the vector as giving you like a fluid, like think of the arrows as representing the, like, yeah, there's actually, this is similar to, yeah, like this is how like some the electric fields and magnetic fields look like, depending on like if you have like a wire or things like that. So if you think of, but usually the analogy that's more convenient, also because the arrows I guess are blue, is that if you think of the, you know, of the XY plane as being some sort of river, like this would be like the arrows giving you the velocity of the river, right? So if you look at this animation, the it looks like the, you know, it looks like the water is sort of spinning around the origin, right? So the curl, sort of the fact that the curl is not zero tells you that sort of somehow detects that this spinning was happening. And if you look at the curl, it only had like an entry in the third component, right? Our curl was 0, 0, 2, right? And I don't know if you have computed ever like angular velocity with this right-hand rule also. There would be like, there's some sort of like, the curl is sort of pointing in the z-axis, which is sort of like how you assign, like if you were to assign like angular velocity, like, you know, if imagine like you put like a paper boat in one of these like arrows, so it starts like maybe spinning in like in circles, in fact, and like the angular velocity that boat would have like is completely along the z-axis. Is that making sense? So the curl is also related to some sort of like angular velocity. So the fact that the curl is not zero is somehow telling you that there's like some spinning going on. Is that okay? And then you can compute that like for something different, like x, y. No, this one is not conservative because the third entry was not zero. But if you change it to like xy, you see there's no longer like, it doesn't look like there's like any spinning going on this fluid. And so in fact, if you want to try it, you can check for the curl of the vector with x, then y comma 0, its entries is 0, 0, 0. So well, we can do it quickly. And so this one, like the one that I'm about to show you, will be conservative, the next example. So if you take f to be xy0, then the curl of f what does this give you? It gives you I partial with respect to y of 0 minus partial with respect to z of y minus k, sorry, minus j partial with respect to x of 0 minus partial with respect to z of x plus k partial with respect to x of y minus partial with respect to y of x. Is that making sense? So if you look at this formula, all the entries become 0. So you get 0i plus 0j plus 0k. So this one is 0, 0, 0. And since all the entries vanish, this vector field is conservative. So this f is that okay?
So in order for f to be conservative, it has to be 0, 0, 0.
Yes, it needs the 3 to be 0, correct. And in fact, just to go back to the animation, if you look at this this vector, or you could also do it with minus the flipping both entries. This is like what is known like as a radial vector, right? And this is like in fact like sort of if you place a mass at the origin, this is sort of like how the gravitational attraction created by this mass would look like, right? Like the arrows are pointing towards the mass. Or I don't know if you have seen like this and like illustrations like for the electric field that a proton creates, right? If you place a proton at the origin, that's like the electric fields are sort of radial, pointing outward because the charge is positive. And so this tells you that the electric field that a proton makes is like, for example, conservative. And so what that means, like this is the next step. The fact that it's conservative tells you can find like a potential function, which is like what you would call the electric potential, like in chemistry, or like, or if you have like a battery or things like that. Those are like the things related to voltage and things like this. But that's the next step.
Wait, sorry, but so based on the graph, if the four arrows are either pointing inwards or directly outwards from the origin, that would make it conservative?
In both case, like well, in this particular case, if I can reverse the sign, right, in both entries, right, and use minus x minus y, this is also conservative. Because like, you can like, there's like, let me write it. So there's sort of like you can pull out the minus sign, right? Like, so if think of this way, if G, right, what would be the curl of minus f, right? By that I just mean that you change the sign of each entry. That should be minus the curl of f. This actually works, and so this happens to be 0, 0, 0. Because like this curl is basically just computing partial derivatives, right? So like you can pull out like a partial derivative from the constant, right? Or if you were to say what's the curl of 2f, right? That's 2 times the curl of f. So that's still 0, 0, 0. Is that making sense? And yeah, so the next step is that we're going to find a potential function. So like, let me explain what that means. So this is the second step. If f happens to be conservative, then one can find a potential function for f. One can find we're going to use a notation in math classes. Like in physics classes, sometimes it's called like V for volt, like, for voltage, or U for potential energy, right? Maybe you have seen those too, but. And so, and this is like a function. This is a function. F, which satisfies. Here's the key condition. The condition is that if you take the gradient of f, then you get like the vector back. So we're going to like, what I'm saying is that if your force happens to be conservative, you can find a function with the property that its gradient gives you back the force. Okay. So just to give you like, hopefully this will look familiar, just as an example. Imagine that, like I'll show you how to do this, but imagine that this, I gave you this formula. I don't know if this looks familiar. This F formula looks familiar to some of you. Sorry, I should put like a Y here. Oops. Sorry. I did it wrong. It was a J, what I wanted here, so 0 minus mg. Does that look, now, does that look better? And this is like the force that acts on a, right. This is like a force that would act on a falling mass, right? Under like a constant gravitational field. This is like the type of things that you do in projectile motion, right? So in this case, the formula for the potential will end up being minus mg times y, because the gradient of f if you use the formula for f, the gradient of f will give you 0 minus mg comma 0. So it is essentially the potential, like the formula for potential energy that you know from physics. It's just that the sign is opposite of the one that the physicists use. So there's like a sign convention which is different, because for them, like the gradient is minus the force, and for us the gradient is the force. Like this is a very annoying discrepancy, but like, so the potentials that we find in this class are minus the potentials that you find in the physics classes. But I'm just saying that like this sort of, like what I'm trying to say is that this is actually the stuff that you know, okay, like, or may have seen before. So how to find f? Yeah, so this is like the potential energy, right? And in order to find the potential function, like what we're going to do is sort of solve like a system of equations. You must solve, because remember, what's the gradient? Oh, sorry about that. Yes. Good. So remember that the gradient of a function was just the partial derivatives, right? Like partial with respect to x, partial with respect to z, and partial with respect to y. So what I'm saying is that the potential function is basically cooked up so that those partial derivatives agree with the entries of the force. Yeah. Like, because, you know, if you have like a cost function and things like that, the derivatives or the gradients are like marginal utilities, right? Marginal cost. So, you know, yeah, like there's like, there are analogs of such things for economics. There are like even Lagrange multipliers like are used in economics, right? For optimization problems and things like that. But yeah. So good. Glad to hear that. So let me do an example where I show you how to find the potential. Well, now hopefully you understand it better. So let's find a potential for, so let's consider this example. So I give you this force, okay? And like just as a remark, you can check that the gradient of this force will, the curl of this force will be 0, right? So remark, check that the curl of F is 0, so that F is actually conservative. Okay, so like strictly speaking, you first have to convince yourself that you have to verify that F is conservative. Okay, so let's say you do that. So now that you know that F is conservative, you can spend some time trying to find the potential. Okay. So let's find the potential for F. Oh, good. Well, I'm glad that you're introducing mathematics into your dinner conversations with your families. So what we need to do is we must solve well, although these vectors are called conservative, so maybe you then shouldn't mention this then. Okay. So again, like basically what I do is just copy the entries of F, right? This is the first entry, this is the second entry, this is the third entry, and that should agree with the partial derivatives of this function we're trying to find, okay? So here's like an analog of what I'm about to do. So here's like something for you to compare it with, right? So here's an analogy. If I had asked you to find a function whose derivative was like x squared plus 1, what would you do to do this, right? How would you find F in this case? This is like the baby case of what we're about to do. You integrate, right? So you say F is like x cubed over 3 plus x plus a constant of integration, right? But like the key was integrate with respect to the variable, right? So essentially, we're going to do the same. We're going to do like partial integrals where we integrate with respect to the variable that we care about. Okay. So again, like this is similar to Lagrange multipliers in the sense that you have like a system of equations. You can really start with your favorite equation. Here, there's not too much of a difference. Like in Lagrange, sometimes it was easier to begin with one equation over another. But here it's just like integrating, and typically there's not too much difference in difficulty between the different integrals that you have to do. Well, f is like the entries here are always given. Yeah, these entries are always given. So like what you need to do is sort of find the system, solve the system. So like for one, like you can start with one and you do like a partial integral with respect to x. So think of these like these are not like definite integrals. They are more like indefinite integrals from the ones like you did in Calc 1. So what like again, this is similar, but it's similar to how we were computing integrals before. Like when you do this, like you're pretending that y or z are like constants, right? So what would be the integral in this case? Good, is x squared ln. Is this step making sense to everyone? Because again, like you just have to pretend that everything else is like a constant, except for the variable you're integrating against. But here comes the key step. So usually we would write like plus z, right? Where z is a constant of integration, right? Like a number. But what did we consider a constant when we did this integral? What like you know, for example, yeah, so things that involved y were taken as constants, right? So like what I'm trying to say is that it actually like the constant of integration is not really like a constant because it could have depended on y. And if there had been like a z, there would also have been like a dependence with respect to z. Because what I'm trying to say here is like when you did this integral, you sort of pretended that y and z were constants, even though like in this particular case, z was not present, but like in general, like the two variables that you didn't use would have been treated as constants. So like what another way of what I'm trying to say is that if you still take the partial derivative of f with respect to x, this term goes away. So it is still one continues to be satisfied. So here, like really, our constant is a function of the is a function of all the variables we didn't use for the integration. Is that making sense? Yeah. Why? That's why constant is in quotes. Because like in the eyes, in the part of the partial derivative, they were treated as constants, right? Or the partial integral. Okay. So think of this almost like for those of you who have made like who have programmed work with programming, like do some coding, right? So we had no idea of what f was at the beginning, right? F, we didn't know what it was. Now we have updated our information because now we know f is sort of this form, right? So like our candidate has like now we know a little bit more about f. So like f, we know this is like the new version of f, right? we know that the f, whatever it is something like this, right? So this is like step one of the program. And now you just have to feed it into the other equations, right? So think of this as doing like an update on your information on what f is supposed to be. So at the beginning, f, we had no idea. After the first step, we know a little bit about f, and then we just keep going. So for example, if you look at equation 2, right? This is what equation 2 said. Right, because we still have to solve the system of equations. So we still need to go back to the other equations, right? But the idea is that now you can like use this information for what f should be. So really what you're trying to find is that the partial derivative with respect to x squared ln plus z of yz is x squared over y plus z squared. Is that making sense? Because now we have a better candidate for what f should be. So I'm just plugging that f. It's like a substitution. Think of it like you substitute f into the other equations. Are there any questions up to this point?
Sorry, can you scroll back up to the system one more time so I can see?
Yes. The system had, can you see it? Like, let me zoom out. The system had, in equation 2, the right-hand side was x squared over y plus c squared, correct? Can you see that?
Yeah.
So what I'm saying is that, like, we used the first equation to have a candidate for f, right? So we know that f, our candidate, is supposed to look like this. And then I just plug that into the other equations, okay? Is that making sense?
I still am struggling to see where you plugged f into.
Well, I plugged it into the left-hand side.
Okay. Yes.
Right?
Okay.
Right,
Yes.
because the left-hand side refers to the partial derivative of f. So I just replaced what, if you look at this step, here I just copy pasted the equation 2. This is literally how equation 2 was written, but I'm now plugging into f, like, you know, I'm making this substitution.
Okay. Yeah. Yeah. I see.
Is that okay? Is that better now?
Yes. Thank you.
Good. And so, and then what you see is like there's x squared over y on both sides of the equation. So you just get an equation for the partial derivative of this function z with respect to y. Okay. And then like, again, like you get like an equation involving a function and a partial derivative. And so how would you solve this equation? You have to solve it exactly the same way as before. So what should you do in this case? Integrate. Good. So with respect to what? Y, because this is like a partial derivative with respect to y. And what do we get here? If you do this partial integral. Good. Or let me write it as yc squared. Okay. And then what do we have to put now? Plus a constant of integration, right? But yeah, but this is now where it's getting better, right? Okay, so first let's not call it Z because I'm already using Z. So let's call it B. Because otherwise it would be too confusing, right? So I'm going reverse alphabetical order. But what else can we say? Like, yeah, what you would like to, maybe you would think, well, this should be like a function of X and Z, but actually we had already integrated with respect to X. So you can sort of forget about X, right? This is why another way to say this is that implicitly we're assuming that C is just like a function of Y and Z. And so like this constant of integration is just really like a function of Z. I will use the British pronunciation. What I'm trying to say is that there's no longer like a need to put X as one of the variables that on which this constant could depend or function, because like you already integrated with respect to X at the beginning in the first step. Is that making sense? Like think of this, like we started with 3 variables, X, Y, and Z. We integrated with respect to X, and so that leaves you 2, right? And then we're integrating, and so that's why the constant could depend on 2 variables. But now we are integrating with respect to a new variable, so that leaves you 1 variable left. And so that's why the constant can only, now the function can only depend on the remaining variable. So like, you know, the constants of integration can only depend on the variables you haven't used, basically. Is that okay? Is that making sense? And so what do we do now? We do like a version of F 2.0. So this is version F version 2.0, where it's just is what we had before. But now we substitute this formula with what we just found. So is that making sense? Yeah. Scroll where? Oh, scroll down. But you see, like, this is why it's like a program, like you're feeding like into the machine something, but at the end of the process, like you get more information. Any questions up to this point? So far, so good. So here's the last question that we haven't used, right? And again, just to go back for a second, if you copy paste the last equation, we have that. But again, I'll substitute this new upgraded version for F into the system. So okay. So we get 2yz. Well, we get 0 plus 2yz plus dv dz equals 2yz. It will always work starting at 1. Yes, you can always start at 1. It doesn't matter where you start. Yeah. The only difference, like for example, is like, say, if you start at 2, right? If you start at 2, like the integral that you do first is with respect to y. So the function, the constant that you get can depend on x and z, right? So like the dependency of the variables of the constant change depending on where you started, right? Because the dependency is always on the variables that you didn't use for the integration. But if you want, you can always start with 1, so that like it's always the same on what variables the constants depend on. So right, you can, if you prefer, like, because now this is like a function just of one variable, there's nothing wrong with just like writing this as like a partial derivative. That's totally fine. There's no difference between partial derivative and ordinary derivative in this case, right? Because B only depends on C. So like, yeah, but it's, yeah, if you want for consistency, we can just like keep using the partial derivative. And so what is V? V would be like the integral of 0 with respect to Z. And so what is that? It's 0 plus a constant, right? And that's like, now this is literally a constant. So this is like 0 plus A. But now A is like an actual number because B had nothing else, no other variables on which it could depend, right? We started with X, we had two variables left. Well, then we did Y, we had one variable left, and then we already did Z, so we have 0 variables left. So it's just like a number. So this is like an actual number. Is that making sense? And so our final update for F, the final version of what F is supposed to be, is that F is x squared ln plus yz squared plus a, or this is like just like an arbitrary constant. Oh, I is that like for some reason, like I never, yeah, like the settings on my iPad, I never like synchronize them, so it's not, yeah, like the dates are completely off. It has been suspended for the entire semester, actually. So it's actually January of early this year. So it's like a version of my past, like my past self coming now. Yeah. Like maybe you have heard this, but if you look at these physics classes, they always tell you that you can set the potential energy to 0. That you have, when you choose like a potential energy, you choose like a reference at height, right? So this is like related to the fact that there's like an ambiguity in the sense that there's like an arbitrary constant when you find the potential. You can never like sort of finish fixing, like you have to like fix it, like say, okay, I want A to be 1 or 0 or 2 or whatever. So there's like there's a choice on where you want to, like, you know, it's like the analog of the choice on where you want to make the potential energy, the gravitational potential energy 0, right? Because you have to make a choice or where for the height. So, but like the point is that this is a potential, because if you find the gradient of F, like this is so much easier, right? If you just take the gradient of F, you get 2x ln of y, x squared over y plus c squared, and then you get 2yc. And these are, if you go back to the beginning of the problem, these are precisely the entries for F. So we did succeed in finding a potential function. And is that making sense? Yeah, just like by taking the partial derivatives. But I'm just saying that it actually, like, it's like a sanity check, right? Because if you take the gradient, you should get back the vector that you started with at the problem at the beginning of the problem, right? So this is good. Well, it looks like, I don't know if it's a tongue or a cigarette, so maybe I should eliminate the tongue so that. So far, so good. Anyone else? Any more questions? It should the gradient. If you are claiming that this is a potential, the gradient should give you the original vector that I gave you. Yeah. Yeah. Otherwise, you didn't succeed in finding the potential function. Okay. And here's the moment everyone, well, maybe it's not clear that this was a key moment of today. Why are we doing all of this? Because, well, it's what people would call V. Yes, remark F is V, where this is like V is a notation physicists use for potential. So our like what I'm trying to say is that our potential is off by a negative sign from what the physicists write. Long story. So like if we find a potential in your physics class, you should multiply everything by -1, and that's like the potential the physicists want. So it's like an overall sign difference. And here's like why did we do all of this? Because like the idea is that like the reason for doing all of this stuff is that once you know the potential, the finding the work is super easy. So knowing the potential makes finding the work a trivial matter. It's like it's entirely like uncomplicated. So this is essentially why we did this. So what I mean by that is that remember that like the thing we started with is that maybe you had like a point, like imagine that this is where like the box was located at point P. You want to go to point Q. And so you choose like a path, and it can be like a crazy path. So you want to find the work of F along this path, right?
It would be just a difference in potential.
Yeah, it's just a difference in potential. When F is conservative, right? So what I'm saying is that the work just happens to be like the difference in the potential functions. Like you evaluate the potential at the final point minus the potential at the initial point, and that's just the answer for the work. And so you see, it only depends on the endpoints. It does not depend on the particular curve that I wrote. So the work equals like difference in potential function. Yes, let me let's just apply it to this example. So for like say let's say that like in our example, right? So let's say that F was this, and I'm about to finish. Like I may go 2 more minutes. So if feel free to leave if necessary. But I'm almost done with today's. It's just to conclude this topic so that we can start with a new section next time. So imagine that you wanted to take this from the point P, you wanted like to find the work done by this function from the point P to the point Q. And again, these are completely random points. I'm just making like an example. So like, let's say P was like 0, 1, 0, and Q was 1, 1, 1. And again, you take your favorite path in the world. And so what is the work in this case? Well, remember the work done by F. Since we had found that the potential was x ln of y plus y c squared plus a, right? The work is just F evaluated at Q. So F at 1, 1, 1 minus F evaluated at 0, 1, 0. So F at 1, 1, 1 gives you 1 ln of 1 plus 1 plus A. And F of 0, 1, 0 gives you, let's see, what? Oh, yeah. So should I have made ln of 1 is 1, right? So let's make this point E. Oops. Oh, yeah, no, sorry. That's stupid me. That's fine. Let's keep it 1, 1, 1. So it's, yeah. Right, so this is just what you get by plugging 1, 1, 1 into F. That's like the first term, right? Let me put it in parentheses. And then you're subtracting what you get by plugging 0, 1, 0 into F. And so ln of 1 is 0, so you get 1 plus A minus A, and so you get 1. So in this particular example, the work is just 1. So you see, like the constants cancel in the same way in which when you evaluate like a definite integral, the constants cancel. So that's why it doesn't really matter which choice you made of A. But like that's how in practice you always find the work once you know the potential function. Okay. So next time, sorry.
Is there a unit on that?
Well, if you thought like physically, this would be like joules or whatever, but like, for our class, we won't use units, but yeah, like if you actually thought of F as a force, then this would be in units of energy, right? This is why the potential is called potential energy, right? Because
And
it would have,
would those units be, I guess, like defined in the
right?
Would those units be defined in the equations that we were given?
Could you repeat it again? I think I cannot hear you.
Where would those units like be defined? Would that be like the original equations?
Yeah, it would be defined when you're given like the function for F. Yeah. So, but again, like we never use units, but if you were to give units, like, sorry, if you were to give units, like, yeah, at least typically would end up with units of joules, right?
Okay.
Is that okay? So next time we'll start again, like a new topic, which is almost one of the last topics for the next midterm. So I'll see you on Monday, if that sounds good.